If you have ever tried building an interactive world model, the dirty secret, after about 3 minutes of generation, your pristine simulation inevitably turns into this warped, smudgy nightmare.
Oh, absolutely. It just completely falls apart.
Yeah, it does. So welcome to AI Paperslop. Today, we are looking directly at LingBot-World 2.0, which is also referred to as LingBot-World-Infinity, by Zelin Gao and the research team at Ant Group and Robiant.
Right. Getting right into the architecture here. LingBot-World 2.0 is an interactive, causal video generation world model, and it's designed to fundamentally solve that exact drift problem we just mentioned, the one found in older autoregressive setups, like Genie 3 or Happy Oyster.
Okay, so how are they doing it?
Well, the architecture introduces 4 major structural upgrades. First, they achieve an unbounded interaction horizon, meaning you can sustain continuous generation for hours with 0 visual degradation.
Wow, hours. That's huge.
Yeah. Second, they hit real-time inference, specifically 720p at 60 frames per second by utilizing a highly distilled student model. Third, the interaction space is massively expanded. We're talking high dynamic semantics like archery, spellcasting, on-the-fly weather changes, rather than just simple camera panning.
Right.
And fourth, they deploy this agentic harness around the base model. It uses a dual agent pilot and director system to continuously orchestrate the world state.
Okay, so if you are an AI researcher or an ML engineer listening to this, you already know that making a model output a coherent 5-second video is, it's essentially a solved problem at this point.
Yeah, definitely.
But keeping that video temporally stable for an hour, especially while a user throws asynchronous dynamic control inputs at the latent space, that is a completely different challenge. Yeah. So today, we are doing a deep dive into the exact architectural data and distillation pipelines the authors use to actually achieve this real-time stability.
It really is a fascinating pipeline.
It is. But to understand the fix, I think we have to look at the root mathematical cause of why previous causal video models fall apart. Like, we know the model is predicting the current state based on previous visual states, but how are the minor step errors compounding so catastrophically?
Well, it's an inherent flaw in autoregressive feedback loops. When your model infers the current frame, that prediction is, at the end of the day, a statistical approximation.
Right.
It contains a marginal, often imperceptible deviation from the true data manifold. The problem is that this slightly flawed output tensor is immediately fed back into the model as the ground truth context for the very next step.
So it trusts its own mistakes.
Exactly. Because the model treats its own previous approximation as absolute truth, those deviations stack. The conditional distribution shifts slightly with every single step. So over a long horizon, the geometry warps, the textures smear, and the latent representations just drift away from any recognizable physical reality.
Yeah, and that compounding error has to be especially fragile when you start injecting complex user inputs.
I noticed, actually, that they inject camera controls, but they ditched standard Euler angles or XYZ coordinates for Plucker embedding.
Yeah, they did.
So why incur the computational overhead of calculating 6-dimensional viewing rays for every pixel just to pass a camera pose? That seems intense.
It does, but standard 3D coordinates are notoriously problematic for 2D diffusion processes. They suffer from gimbal lock and discontinuity in the rotation space.
Right, the math gets messy.
Exactly. But Plucker coordinates represent a line in 3D space, specifically the viewing ray of the camera, using a 6D vector that combines direction and momentum. So by encoding the camera pose this way, you give the diffusion model a continuous, mathematically stable representation of how the 3D geometry should project onto the 2D pixel grid.
Okay, that makes sense. And how does that actually integrate into the network?
Well, they take these 6D coordinates, pass them through an MLP, and then integrate them into the diffusion blocks using adaptive layer normalization, or ADLN.
All right, so this means the scale and shift parameters of the self-attention layers are directly modulated by the precise viewing rays. It literally forces the model to respect the camera geometry frame by frame.
That is incredibly precise. And they're also feeding in chunk-wise text prompts alongside that ADLN modulation, right?
Yeah, exactly.
But having highly precise condition injection doesn't really solve the core drift problem if the model learns bad habits during pre-training. Like, standard teacher forcing models fall into a really specific overfitting trap when they're exposed to long contexts.
They absolutely do. During standard teacher forcing, we train the model by providing perfect, uncorrupted historical frames to predict the next frame. The loss function optimizes for that specific one-step prediction.
Right.
In short sequences, this forces the model to learn transition dynamics. But as you scale up the context window to process much longer sequences, the model realizes, hey, I can minimize the loss just by copying features from this highly detailed, perfectly clean historical context.
Instead of actually figuring out the future.
Exactly. Rather than doing the hard work of actively modeling the complex transition into the future, it just over-relies on the past.
It's sort of like a driver relying so heavily on the rearview mirror that they just completely forget to look through the windshield.
That is a perfect analogy, yes.
So it is minimizing loss through feature matching rather than true causal prediction. And then when you deploy it at inference time, and it has to generate its own future without that clean ground truth, it just completely collapses.
It falls apart entirely.
So to fix this, the authors introduced the mixture of bidirectional and autoregressive attention mask, or MOBA. But wait, if they are appending a bidirectional mask to an autoregressive generation task, aren't they technically violating the causal constraint? I mean, how does a model look forward in time without cheating on the inference side?
That is the really clever part of the MOBA implementation. They are not making the entire attention matrix bidirectional. They just take the standard lower triangular causal mask where tokens can only attend to past tokens, and they modify just the bottom right block.
Oh, just the bottom right?
Yeah. They append a bidirectional component specifically to a localized window at the very end of the sequence during training. This localized full attention block acts as this powerful regularizer. It forces the network to reconcile past context with future states simultaneously, but only within that specific block.
Okay, so it prevents the attention heads from collapsing into just passively reading the historical tokens.
Exactly. It mathematically tantalizes the model if it abandons its forward prediction capabilities. By forcing bidirectional consistency in that local block, the model has to learn robust transition dynamics. It learns how pixels actually must evolve over time rather than just copying them from the past.
And then at inference time.
When you switch to pure inference, you revert to a standard autoregressive rollout. But the weights of the attention layers have been regularized to actively predict rather than passively copy. And that is the actual mechanism that halts the long horizon visual degradation.
That is a brilliant trick. But, I mean, a stabilized attention mechanism like MOBA is critical, sure, but the weights are only as good as the data they are optimized on.
Oh, 100%. Data is everything here.
Right, because if a user triggers a highly dynamic event, like, say, a character casting a spell or driving a vehicle that displaces water and creates a wakeout, the model has to actually know the temporal physics of those pixels. So where are they sourcing data with that level of physical and temporal alignment?
Well, they constructed this multi-granularity data engine. It's categorized into 3 distinct pillars to ensure the model doesn't overfit to just one specific type of visual distribution.
Okay, what's the first pillar?
The first pillar consists of egocentric videos. This is your first-person perspective footage, which is completely indispensable for teaching the model intricate hand-object interactions and spatial proximity.
Right, grabbing things, holding tools.
Exactly. Then the second pillar is synthetic data rendered from game engines, like Unreal Engine.
See, that seems mandatory to me. Trying to extract perfectly clean, temporally aligned action signals, like the exact bounding box of a character jumping, or the collision trajectory of a vehicle, trying to get that from raw, compressed web video, just seems nearly impossible. The noise-to-signal ratio is way too high.
You're totally right. Synthetic data gives you absolute ground truth alignment. You have the exact depth map, the perfect camera pose via those Plucker coordinates we discussed, and the precise control input registered at the exact millisecond the pixel changes.
So it connects the button press directly to the physics.
Exactly. The model learns the pure causal link between the user pressing jump and the character's geometry actually displacing upward. And then the third pillar is massive scale web video.
The general internet video.
Yeah, it acts as a regularization data set. It exposes the foundation model to the open domain long tail of visual distributions. That ensures your generated world doesn't suffer from that plastic synthetic texture bias that's super common in pure game engine data sets.
Okay, the structural mix definitely makes sense. But the annotation strategy is where things usually break down with video, right? Like, if you have a web video of a horse rearing up in a field while it rains, a standard vision language model will just generate a global caption like a brown horse rearing in a rainy field.
Right, which is totally fine for standard text to video.
But for a system that requires real-time, zero-latency user controls, that global caption seems useless. If the user hits a hotkey to change the weather to sunny on exactly frame 40, A static global caption gives the model no mathematical correlation between the text token and the frame-by-frame temporal change.
Exactly. To solve that temporal ambiguity, they implemented a multi-track annotation pipeline. So they run the raw video through a technical profiling stage first, just to drop corrupted frames. But then they deploy a VLM to generate chunk-wise local captions that are decoupled into distinct event tracks.
They coupled how?
They isolate the semantic elements of the scene mathematically. So you have an independent track for motion, an independent track for character interaction, and an independent track for environmental dynamics.
Oh, wow. So they're essentially structuring the text conditioning like stems in an audio mix.
That is a great way to put it. By decoupling the tracks, the model learns the precise causal relationship for each element independently.
I see.
Because think about it. If a character swings a sword, and simultaneously the lighting shifts because a cloud covers the sun, a single global caption would entangle those two visual changes. The attention heads might falsely correlate the action of swinging a sword with the sky suddenly darkening.
Right, which would be a weird hallucination during gameplay.
Exactly. But by separating the interaction track from the environment track, the cross-attention layers learn exactly which text tokens are responsible for the character's geometry and which tokens are responsible for the global illumination.
That makes total sense. So decoupled event tracks solve the temporal ambiguity during pre-training. But precise causal conditioning generally requires heavy multi-step denoising. If you're rendering a 60 FPS game environment, running, say, 50 denoising steps per frame is going to completely bottleneck the pipeline.
Oh yeah, it would be impossible. Generating the latents alone would take way longer than the 16 millisecond frame budget.
So how do they bypass the multi-step requirement to hit 60 FPS without losing the causal precision we just established?
They apply a highly aggressive two-stage distillation process to compress the pre-trained teacher into an incredibly fast student model.
Okay.
The first phase is consistency distillation, or CD. The core objective of CD is to drastically reduce the number of function evaluations, or NFEs, required to sample the diffusion model.
So basically skipping steps.
Right. Instead of the student taking hundreds of NFEs to numerically solve the probability flow ODE trajectory, like the teacher model does, CD enforces a consistency loss. This trains the student to map any point on that ODE trajectory directly to the boundary condition.
I see. So it's giving the model a mathematically proven shortcut across a maze, rather than forcing it to calculate every single turn like the teacher model does. It maps the noise latent directly to the clean target in just one or two steps.
Exactly. Preserving the action condition dynamics the teacher learned, but executing the mapping exponentially faster.
Well, that solves the inference latency. But doesn't a fast, heavily distilled student model compound errors significantly faster during an autoregressive self-rollout? Like, if you are jumping across the ODE trajectory in one giant step, your approximation error has to be inherently larger.
It is. That's the critical trade-off.
Right. So any slight deviation from the data manifold during step one is going to be wildly amplified when that frame is fed back as context for step two. So if consistency distillation actually accelerates the drift, how are they recovering the stability?
That is where the second phase comes into play. Distribution matching distillation, or DMD. DMD optimizes the student generator by minimizing the KL divergence between the distribution of states generated by the student and the true data distribution.
Okay, but how does that stop the compounding error specifically?
Because of how they apply the DMD loss. This is the implementation detail that defines LingBot-World-Infinity. They do not apply it over teacher-forced states. They apply DMD over long, autoregressive, self-rollout trajectories.
Wait, really? Meaning they force the student model to run inference on its own, allow it to accumulate those slight step errors and drift off the manifold, and then apply the loss gradient.
Yes. They force the student to generate extended sequences using its own previous predictions as context. By applying the DMD optimization on the state distribution induced by the student's own generated trajectory, the model explicitly learns a self-correction vector.
Oh, wow. So it learns the mathematical penalty for drifting.
Exactly. And it adjusts its weights to continuously pull its predictions back toward the true data manifold, even when it's conditioned on its own noisy past. This specific mechanism is what allows the distilled model to sustain verified, hour-long continuous generation at 60 frames per second without that geometric collapse.
It essentially learns to clean up its own accumulated noise distribution on the fly. That is rigorous. But, a lightning-fast, highly stable foundation model is still just a matrix of weights. A diffusion model doesn't autonomously explore a map. It just sits there waiting for a tensor.
Right, it doesn't play itself.
Exactly. So to turn this into an interactive simulator, you really have to build an architecture around the model to handle the state logic, right? Like coding assistance, where an LLM needs a terminal environment to inspect state and act.
That's spot on. The researchers actually wrapped the generative core in what they call an agentic harness. It consists of two distinct asynchronous modules, the pilot agent and the director agent.
Okay, what does the pilot do?
The pilot agent handles tactical execution. It reads the current visual state and the immediate user inputs to determine localized character physics, stepping forward, blocking an attack, picking up an item. It feeds those localized control signals directly into the generation pipeline.
And the director agent handles the global state.
Exactly. The director is powered by a visual language model, and it's acting as the overarching game master. It surveys the generated world context and synthesizes fresh macro-environmental events to ensure the simulation actually remains dynamic over a long horizon.
So it keeps the game interesting.
Right. It proposes structural shifts like transitioning the biome from a desert to a snowstorm or spawning a sudden enemy encounter. These director proposals are actually routed to the user interface as dynamic hotkeys, allowing the user to trigger massive environmental shifts on demand.
Okay, but think about the latency there. If the user hits a hotkey to trigger a snowstorm, the control signal hits the conditioning layers immediately. But how does the system architecture handle the visual latency? You cannot have a 200 millisecond stutter while the VAE decodes the latents into RGB pixels. 60 VPs requires a frame every 16 milliseconds.
It's a massive engineering hurdle. To solve it, they engineered an asynchronous latency pipeline that completely decouples the latent generation from the image decoding.
How does that work in practice?
The base model continually generates the latent tensors in the background based on the control stream. It does not wait for the VAE. Those latents are just pushed to a buffer.
Okay.
As the VAE asynchronously decodes those latents into RGD frames, the system streams them to the client. But to ensure they absolutely lock in that 60 VPs target and hide any network or decoding latency, they utilize a spatiotemporal refiner that's optimized via TensorArt.
So TensorArt is handling the upsampling and interpolation at the edge.
Yes. The refiner takes the lower resolution decoded frames, upsamples them for spatial sharpness to hit native 720p, and then it synthesizes intermediate frames to bridge any temporal gaps caused by the asynchronous decoding.
That's incredibly smart.
By pushing the interpolation to TensorArt, they maintain a buttery smooth visual output, while the heavy latent generation operates asynchronously in the background.
Well, that definitely solves the compute latency,
Yeah.
but it brings up an immediate bottleneck regarding memory constraints. Like, if you are generating a continuous, highly detailed world for an hour, your context window is expanding infinitely.
Oh, absolutely.
The key value cache, the KV cache, that stores the intermediate attention representations of all those historical frames, it would exponentially explode in size. You cannot keep an hour of 720p, 60pp's feature maps in VRAM. The system would and crash in 10 minutes.
You're completely right. Maintaining a linear KV cache is basically impossible for unbounded generation. So the authors bypass this using a dynamic KV cache management system.
How aggressive is it?
Very. The architecture aggressively prunes the cache on the fly based on semantic relevance. It evaluates the current control signals and the immediate spatial state, calculating the attention scores to determine which historical tokens are actually informing the current generation.
So it just dumps the rest.
Yep. It selectively retains only the most informative history while actively discarding stale, low-attention entries right out of the VRAM.
Okay, let me make sure I have this. So if my character walks out of a tavern and enters a dense forest, the system looks at the current environmental control inputs, evaluates the attention weights, realizes the tavern's indoor geometry is no longer relevant to rendering the forest, and just evicts those specific tokens from the KV cache.
That is exactly how it works. The dynamic pruning keeps the memory footprint strictly bounded. That ensures stable throughput regardless of how many hours the simulation runs. But there's actually a secondary benefit. It actively reduces visual hallucination.
Really? How so?
Well, by evicting stale tokens, you prevent old, irrelevant semantic concepts, like, say, the wooden textures of that tavern, from accidentally bleeding into the cross-attention layers when the model is just trying to render the leaves in the forest.
That is a phenomenal engineering solution for throughput. But, evicting historical tokens from the cache completely exposes the most fundamental limitation of this entire paradigm. If you aggressively prune the KV cache and throw away the mathematical history of the scene, you entirely destroy object permanence.
You do. And the authors are transparent about this in the limitations section. Because of the dynamic cache management, the model lacks absolute long-term memory.
Right.
It maintains persistence in general appearance based on the VLM's semantic tracking, but it lacks identity persistence. If you spend 20 minutes exploring a highly specific village, walk out into the wilderness until the village tokens are pruned from the cache, and then turn around and walk back.
It's gone.
The village you return to will be a newly generated environment. It will match the semantic description of a village, but the specific buildings and NPCs will be different. The model regenerates based on text conditions. It does not remember explicit geometric data.
Which really highlights the absolute boundary between a statistical generative model and a deterministic 3D game engine. And that actually leads to the other major limitation tied to relying purely on pixels, which is the physics. Because all the dynamics are learned from statistical distributions of 2D visual data, the model does not possess an explicit geometric understanding of mass, velocity, or solidity.
Right, it achieves statistical plausibility, not physical determinism.
Exactly.
The model has learned that pixels representing a hand usually stop moving when they intersect with pixels representing a wall. But because there are no underlying collision meshes, you will inevitably encounter artifacts where a character's arm clips directly through a solid object, or two vehicles just merge into each other.
Yeah, because to the diffusion model, they're not solid physical objects. They are just overlapping patches of color probability that basically fail to properly resolve in the latent space.
Precisely.
Which brings us to the ultimate question for everyone listening, and a really serious architectural challenge to mull over as you build your own pipelines. Right now, interactive world models like LingBot-World-Infinity are basically faking reality. They are faking physics, and they are faking object permanence purely through pixel-level probability distributions and aggressive distillation. Right. But what happens when we figure out how to natively entangle an explicit 3D physics engine, actual kinematic solvers and collision, meshes directly into the diffusion latent space? If we can force the latents to obey hard physical constraints and maintain persistent geometric memory, will the next generation of these models stop hallucinating reality and start mathematically calculating it?
I mean, integrating absolute physical determinism inside a statistical latent space is absolutely the next major frontier for interactive simulation. It's going to change everything.
It really is. Well, that covers the architecture and training pipeline behind LingBot-World-Infinity. Thank you for listening to this deep dive, and we will catch you on the next one.